Microplastic destroys beneficial bacteriophages. Plastics, polymers and microplastics in the aquatic environment leak chemicals that destroy the phages. Therefore, bacteriophages cannot effectively limit the growth of harmful bacteria, and thus contaminants. The correlation between the number of phages and the physiochemical properties of microplastics was demonstrated by researchers from the Institute of Physical Chemistry of the Polish Academy of Sciences. The work on the effects of microplastics on phages has been published in the Journal of Environmental Quality. When microplastics enter the environment, there is a layer of biofilm on its surface, which affects the colonization of microorganisms. Various strains of bacteria transported by microplastics can grow uncontrollably, reaching the digestive tract of fish and other animals. Microplastics disrupt the intestinal flora and accumulate in other tissues. At further stages of the food chain, it enters the human digestive system. The average person eats tens of thousands of microplastics every year. Polymers can build up in the body and lead to serious health problems. The findings of researchers from the IPCPR show that the growing environmental pollution with microplastics can negatively affect global ecosystems. Scientists have studied the effect of microplastics on the amount of bacteriophages in the aquatic environment. They used 12 different types of commonly used polymers, e.g. polycarbonate, PC, polyethylene, PE, polymethyl metaacrylate, PMMA, polypropylene, PP. We have selected commonly used polymers to reflect microplastics in the environment. We prepared polymer samples by mechanically grinding larger pieces of plastics commonly available and used in the industry. We tested the effect of substances leaching from polymers on phages in a buffer containing microplastics. The tests were carried out on appropriate plates, after which we used a classic linear regression model to check which physiochemical parameters, 65 variables were tested, affect the amount of phages in the samples, explained Professor Jan Patensny. According to the Institute, bacteriophages destroy up to 40% of bacteria every day. Bacterial biomass. They play a vital role in maintaining the biological balance of bacterial cultures in all environments, from the ocean to sewage. Compounds leaking from polymers can inactivate up to half of the phages. Some polymeric materials generate nano and sub-microparticles that engulf phages. Observed by the team of Professor Jan Patensny, a decrease in the number of phages on the surface of microplastics can affect the entire food chain. Getting into water reservoirs. Synthetic materials are easily mechanically fragmented into smaller and smaller pieces. Small plastic particles float in water reservoirs for a long time and accumulate in them. Microplastics less than 5 mm in diameter, or smaller pieces such as nanoplastics, have even been detected in drinking water and mammalian milk. In lakes, rivers, seas and oceans. Microplastic slowly decomposes, releasing many harmful compounds, from plasticizers, pigments to heavy metal ions. The surface of the microplastic adsorbs various organic compounds, performing the function of e.g. food store for many microorganisms. This leads to an imbalance between the various groups of microorganisms that make up the biofilm. Einstein's theory was put to the test. The results of 16 years of testing have been published. An international team of astronomers used telescopes from around the world to conduct the most rigorous test of general relativity to date. The research lasted 16 years, and as it turned out, Albert Einstein's predictions published in 1915 are still valid today. Dr. Dick Manchester, an Australian National Science Agency CSIRO and member of the research team, explains how this result allows for a better understanding of our universe. General relativity describes how gravity works on large scales. However, the theory does not work at the atomic scale, where quantum mechanics reigns, says Dr. Manchester. We had to find a way to test Einstein's theory on an intermediate scale to see if it was true. In 2003, the Parkes telescope found a suitable space laboratory, a pearl of pulsars. Observations made over the last 16 years have been found to be astonishingly consistent with Einstein's general theory of relativity, exactly 99.99%, Dr. Manchester points out. The discovery was made by a team led by Professor Michael Kramer of the Max Planck Institute for Radio Astronomy in Bonn, Germany. The research was published in the journal Physical Review X. The PSR-J0737-3039A-B system observed by the researchers consists of two pulsars, rapidly rotating neutron stars that emit radio waves like cosmic beacons and create a very strong gravitational field. One star spins 44 times a second, while the other star spins in 2.8 seconds. The pulse of these stars, or their radio emission, is extremely precisely synchronized. Which means that for us pulsars are probably the most useful stars in the universe. They can be used for navigation, probing the interstellar medium and studying gravity. The PSR-J0737-3039A-B system observed by the researchers consists of two pulsars, rapidly rotating neutron stars that emit radio waves like cosmic beacons and create a very strong gravitational field. One star spins 44 times a second, while the other star spins in 2.8 seconds. The pulse of these stars, or their radio emission, is extremely precisely synchronized. Which means that for us pulsars are probably the most useful stars in the universe. They can be used for navigation, probing the interstellar medium and studying gravity. The two pulsars are very close to each other. They orbit their common center of mass every 147 minutes. But because these objects are so dense, their gravitational fields are very strong. Which means they can affect the timing and angle of mutual pulses of electromagnetic radiation beams. Analyses of the radiation emitted by one pulsar in the extreme gravitational field of the other pulsar showed that the photons of the radio waves were slowed down. The strong curvature of space-time also deflected the path of the photons by 0.04 degrees. We tracked the propagation of photons of radio waves emitted from a cosmic beacon, or pulsar, and their movement in the strong gravitational field of the companion object, says astrophysicist Ingrid Stairs of the University of British Columbia in Canada. For the first time, we observed how light is not only slowed down due to the strong curvature of space-time around the companion, but is also deflected by 0.04 degrees. Never before has a similar experiment been carried out with such a large curvature of space-time, he adds. In total, the researchers conducted 7 tests of general relativity. They also tested how the orbital orientation of the binary system changes, and how pulsars affect the space-time around them as they spin. In addition to gravitational waves and light propagation, we also measured the time dilation effect that causes clocks to run slower in strong gravitational fields, explained Manchester. When considering the effect of electromagnetic radiation emitted by a fast-spinning pulsar on orbital motion, we had to take into account Einstein's famous equation E equals mc2. This radiation corresponds to the loss of 8 million tons of mass per second. This may seem like a lot, but it's only a tiny fraction, 3 parts in 1,000 billion of the total mass of the pulsar, he adds. The results join a growing collection of precise measurements of relativistic effects that have so far matched Einstein's predictions. Over the next few years, with the advent of new, more powerful telescopes, we're likely to see even more accurate tests of gravity in general relativity as scientists continue to look for holes in it. General relativity is incompatible with other fundamental forces described by quantum mechanics. That's why it's important to continue testing general relativity as rigorously as possible to discover how and when the theory breaks down. Explains astrophysicist Robert Ferdman of the University of East Anglia in the UK. Finding any deviation from general relativity would be a major discovery that would open a window to new physics beyond our current theoretical understanding of the universe. And it can help us finally discover a theory that unifies all the fundamental forces of nature, he emphasizes.